Swayam Prabha. Digital India. Educated India.
Now let us look at what happens. Say for example, this is a segment of the engine cylinder. This is just one segment. Okay, and what you see, these are the flames. Obviously, the flames will not be very regular shape because in the engine you have turbulent conditions. So what happens? It is compressing. This charge is unburnt charge. This charge is also unburnt charge, and this is pressing this. So the pressure here will be very high. So there may be some sites where auto ignition can happen. Here also auto ignition can happen. So there could be many places where the auto ignition can happen. So if you have an engine where this is the spark plug, auto ignition will normally happen in the farthest corners away from the spark plug. Wherever the flames are reaching the most late, there the possibility of secondary unwanted flame fronts will be the highest. See here, this is 18.83 crank angle degree here, then 19.07. Here it is, everything is clean, but you see here some spots. So that means auto ignition is just beginning to happen. 19.07, this is growing very fast. This is not growing very fast, but this is growing very fast. Quickly it envelops. So this shows that within a matter of half crank angle degree, this is not able to move, but this is able to consume the rest of the charge and explode. This will show you this is a perfect example of visualization of the knocking phenomena. See, don't get confused with this picture. I'll tell you how to look at it. This is the engine, observational engine. Okay, cylinder head from the top. This is the spark plug. Okay, and this is the intake valve and this is the exhaust valve. And this much section of the cylinder head has been replaced with the optical window for photography. So what you are seeing in these pictures is this segment. Okay, and there are two sets of picture, one here, one here. This one is normal combustion, normal cycle, no knocking, and this one is with abnormal combustion. Let's see, this is the cylinder pressure on the y-axis, crank angle degree on the x-axis, and you can see this is very smooth pressure. So this is at 26.6 degree after top dead center, 29.2. It's moving very smoothly. So you can see that this unburnt charge is being consumed very gracefully. It's consumed almost 41.2, 41.6, 45. At 45, everything is consumed. No abnormal combustion is seen in any of these pictures. Okay, and P3 diagram is absolutely smooth. Okay. Now come to the bottom side. Here this is a knocking cycle. So again, pressure on the y-axis and crank angle on the x-axis. So you see here, first image is taken here at this point, second, third, fourth. So up to fourth, in the fourth you see something. Up to 3 it's pretty normal. 3 images are very clean. You see flame front moving gracefully, trying to consume. But then in the fourth, you see the whole thing is just exploding. And once it explodes, whatever this normal, systematic consumption is happening, this is all exploded. Everything becomes very unique. And what you see here is basically, here there is a pressure wave which is moving in this direction. Here once this is consumed, this moves in the opposite direction. And then it leads to amplitudes are different, rate of heat release is different, rate of pressure rise is very different. And what is loose in the combustion chamber? Only the piston. And piston is also hinged at one gudgeon pin, so it will lead to vibrations, and there is no room for piston to vibrate. So actually piston goes and hits the walls on both sides. Okay, it can even physically get damaged. The rings can actually get embedded because of this hitting into the grooves. So many things can happen. many bad things can happen. So this explains, you know, how the knocking can happen and how you detect that knocking. Everybody will have no access to such an engine, but pressure crank-angle diagram, anybody and everybody can do it with little sophistication. So with very, very small instrumentation, you can figure out just by looking at pressure crank-angle data whether your engine is knocking or not. Okay. So let's look at the combustion overall. So there could be normal combustion, and anything which is not normal is called abnormal combustion. What is normal combustion? A combustion process which is initiated solely by a timed spark, that means you are giving a precise timing, and the combustion starts, in which the flame front moves completely across the combustion chamber in a uniform manner with constant velocity. Very smoothly it consumes the entire combustion chamber, it sweeps the combustion chamber. That is absolutely normal combustion, as I showed you in the first set of images. Second, a combustion process in which a flame front may be started by a hot combustion chamber surface wall, either prior to or after the ignition. So abnormal combustion can be anything, it could be starting before you apply the spark, another combustion after you apply the spark, you know, all those are abnormal combustion, or a process in which some or all part of the charge may be consumed at extremely high rates. Okay. So now this abnormal combustion is actually divided into two parts. One is knocking, the other one is surface ignition. What is knocking? A knock which is a recurrent and repeatable in terms of audibility, you can hear it. It's absolutely repeatable. It is controlled by spark advance, so you adjust your spark timing in order to control it. Okay. Advancing the spark timing increases the knock intensity, and retarding the spark reduces the intensity. So normally if you want to control in an engine, in many of the engines, if the knocking is detected by sensors, they automatically retard the spark timing in order to control it. Driver does not come into the picture. Okay. Surface ignition is ignition of the fuel air charge by any hot surface other than the spark discharge prior to the arrival of normal flame front. It may occur before the spark ignited charge, in that case it is called pre-ignition, or after the normal ignition, which is post ignition. So surface ignition can be before the spark, if it is before the spark it is called pre-ignition, surface ignition could be after the spark as well, then it is called post ignition. Okay. So abnormal combustion of any kind is of concern, because when it is severe they can cause major engine damage, and even if when they are not severe they are objectionable source of noise. Okay. So you can really damage your engine if there is abnormal combustion happening. Let us look at surface ignition in a little bit more detail. There are many types of surface ignitions, although it is not very important for the first level course, but I thought I will just explain them to you. First is that, you know, there is a knocking surface ignition. So that means knock which has been preceded by surface ignition. So first there is a surface ignition which is leading to knock. So that is called knocking surface ignition. It cannot be controlled by spark advance, because even if you advance the spark, anyway pre-ignition is starting the combustion before. So by advancing or retarding you can't really control this. Non-knocking surface ignition, so that means surface ignition which does not result in knocking. So surface ignition is happening but not leading to knocking, so that is called non-knocking surface ignition. There is something in between, that is called run-on, continuation of the engine firing after the electrical ignition is shut off. So electrical ignition, if it is shut off, what it will shut? The current to the spark plug. But if there is a surface which is hot, so it will not cut the engine will continue to run. So this is called run on. Okay. There is something called runaway surface ignition. This is very interesting. So surface ignition which occurs earlier and earlier in every cycle. So what happens is, suppose surface ignition is happening 30 degree before the top dead center. In the next cycle it will happen 30.5. In the next cycle it will happen 31. Why? Because you may be generating more and more heat, and that surface may become hotter and hotter and hotter. And if it is become hotter and hotter, it is igniting the mixture earlier and earlier. So what will happen? It can lead to serious overheating and structural damage to the engine. Okay. There are two other types. One is called wild ping. So this is basically knocking surface ignition. So wild ping is knocking surface ignition, which is characterized by one or more erratic sharp cracks. So if there are any sharp cracks somewhere in the structure, it will give you a very different kind of pinging noise. Okay, it is probably the result of early surface ignition from deposit particles. Okay, and then non-knocking surface ignition will give you some kind of a rumbling noise, a low pitched thudding noise accompanied by engine roughness. So engine will not run very smooth, although it is still not knocking, but it's a non-knocking surface ignition, but you will see very low pitch noise, and this is probably caused by high rates of pressure rise associated with very early ignition or multiple surface ignitions. Okay, so this is the entire canvas of abnormal combustions in a SI engine, particularly in the context of SI engines. Now there are some factors which influence the knocking. What are those factors? So the first factor which affects the knocking is compression ratio. The second factor which affects the knocking is engine speed, and the third factor that affects is spark timing. Okay. Now let us look at some of these in more details and how it affects. So for doing that, first let us understand how it happens and how we can really control them and how these factors affect the knocking. So let's see, for example, this is the engine combustion chamber, okay, and you have a side spark plug. Okay, so you apply the spark and these are the flame fronts. Okay, by the time you reach here B dash, this segment has reached the auto ignition temperature. Okay, so now there is a race between this velocity of the flame front and the chemical kinetics of this part. If the auto ignition temperature the ignition delay part of this fuel is large enough so that this is able to penetrate through the entire charge, then it will lead to no combustion event, normal combustion. So you apply the spark here and you will have a very smooth combustion. Okay. If the ignition delay is not really large enough and during that period the flames are not able to move from here to here, and suppose they are only able to move from here to here, so that means this segment C dash D will be the segment where you have already are at the auto ignition temperature and ignition delay period is over. So this will explode. So you will see knocking. Okay. So I think this is just the explanation. So when the knocking happens, there are two flame fronts, they collide, severe pressure pulses are generated, and then these pressure pulses actually get reflected between the piston and the cylinder head. That's what causes the vibrations. Okay. So let's look at some of the factors. For example, there is a time factor which affects the knocking. Time factor, what is time factor? Time factor means if you can somehow increase the flame speed, then knocking can be avoided. Or if you can reduce the exposure of the unburnt charge to the unburnt charge, that will also avoid the knocking. So if you can increase the flame speed or avoid the exposure to the exposure of the unburnt charge so that it does not reach the auto ignition temperature, both of these will lead to reduction in the probability of knocking. How can you increase the flame speed? So one of the very simple ways to increase the flame speed is to increase the turbulence in the engine. How can you increase the turbulence? By increasing the engine speed, and that's in your hand, operator's hand. So increase in the engine speed increases the turbulence and therefore it reduces the knocking, and this is exactly what you do unknowingly when you have knocking and you are driving your motorcycle at 20 kilometers an hour in 4th gear and you experience some metal noise. What do? Intuitively you will reduce the gear to 3rd gear or 2nd gear, and by doing that what you are doing? You are increasing the engine speed, and that increases the flame speed, and that reduces the knocking, right. So, you do it all the time, but this is the reason why you do it. So, obviously, if you have a large engine and if you have a small engine, which engine will have more tendency to knock? Large engine, because in the large engine the flames have to travel longer distances, and this is one of the reasons why you see very large size engines are not made spark ignition. Okay, you will never see a ship engine or a locomotive engine being a SI engine. This will certainly knock. Okay, and small. So therefore, if you look at the spectrum of the engine, most of the small size engines are gasoline engines, and most of the large engines are more compression ignition engines. Okay, combustion chambers are made as spherical as possible. So if you make a spherical combustion chamber mean like this. So if you have a spark here, so this will also reduce the distance of flame travel, length of the flame travel. Okay, so combustion chambers are made as spherical as possible to minimize the length of flame travel, and that's why you see, these spherical chambers are not really available now commercially. What is more popular is something called pent-roof design. Pent-roof design is like this. So it is very close to spherical, and it is most of the modern engines use pent-roof design, SI engines. Then a spark plug is centrally located in the combustion chamber to reduce the flame travel. Earlier people used to locate the spark plugs in the sides, or at I gave you some example. There were like L head engines where here the spark plug is maintained. So this will actually increase the length of maximum flame travel, and this will certainly knock. So you try to locate the spark plug centrally so that the maximum distance is short as possible. And sometimes if there is a problem, you try to locate two spark plugs, multiple spark plugs in one cylinder head, in order to reduce the distance of maximum flame travel, so that this can be avoided. Okay. Second is composition factor. Composition of what? Composition of fuel air mixture. So fuel air ratio and octane number, these are two very important factors which play important role in reducing the knocking. Maximum tendency of knocks takes place for fuel air ratio, which give minimum reaction time. So if you have minimum reaction time in the mixture where the reactions take place very quickly, that will have the maximum tendency to knock. Okay. For example, what kind of a mixture gives you minimum reaction time? Mixture which is stoichiometric or slightly richer than stoichiometric. So you try to avoid that condition if you want to minimize the knock. Second is higher octane number. Higher octane number fuels have lower tendency to knock. Okay, so you should try to use as much higher octane number as possible if you want to avoid knocking. Okay. Third is the density factor. So we have discussed already two factors, time factor and composition factor. Third factor is density factor. Reducing the density of the charge reduces the knocking. If you are having very dense charge, the chemical reactions will be faster and faster, and you want to slow down those chemical reactions in the last part of the charge if you want to avoid the knocking. Okay. Then increase in the compression ratio. What will be the effect of the compression ratio? It will increase the density of the charge, which is going to increase the knocking tendency. Okay. Increase in the inlet temperature of the mixture result in the higher temperature after compression, and this will also increase the tendency of the ignition. So you should try to keep the intake charge as cooler as possible. Then temperature of the combustion chamber walls. If temperature of the combustion chamber walls goes up, this will also increase the tendency of knocking. Right. Reduction in the spark timing retarding the spark timing from the optimized timing result in peak pressures to reach farther downstream of the power stroke of lower magnitude. This tends to reduce the knocking. I will just explain this by this curve. See, this is the pressure crank angle diagram. See, this is pressure, this is TDC, and this is my motoring diagram, and if I apply the spark here, so my pressure diagram will be something like this, right. If I if I retard my spark timing, okay, and I apply the spark here, so how it will look like? So it will look like this. So this magnitude will reduce, the pressure will reduce, and therefore what will happen to the knocking tendency? It will reduce. If I do it here, if I advance it, then what will happen? Right? So higher pressure, higher temperature. So that's why if you retard the spark timing, you will have lower tendency of knocking. Brake torque and power output, but if you want to retard the spark timing, you can reduce the knocking, but then the torque and power output will be the cost that you have to pay. If you decrease the power output, decrease in power output of the engine decreases the temperature of the cylinder and combustion chamber, walls and pressure of the charge. So this will, if you at lower loads, the engine will have lower tendency to knock. At higher loads, the engine will have more tendency to knock. Okay, this reduces the mixture and end gas temperature, which reduces the tendency to knock. Okay. So knock in the gasoline engine is one of the major challenges to design the engine with higher thermal efficiency. Okay, this is what puts the limitation. Otherwise, theoretically we have seen that the efficiency of a SI engine depends on only compression ratio. You can keep on increasing as much as you like, but when you reach a compression ratio of 10, 11, you run into problems such as knocking, and that makes it impossible. So therefore, this is one of the biggest challenge that IC engine designers face. Without knock, an engine can be designed to have higher compression ratio, which will give higher efficiency and power output. So engine designers always try to design an engine which will not knock and still give you highest possible efficiencies with under the given constants. Okay, the demand on the design engineers, the demand to design engineers closer to the allowable knock limit with consequential reduction in the safety limits is highly appreciated. The phenomena is characterized by excessive high pressure amplitudes with stochastic occurrence. The phenomena occurs independent of the mixture formation process in both naturally aspirated and turbocharged engines. This phenomena of knocking is a fundamental issue in modern SI engine design methods. Now I will just like to summarize this whole knocking business with spark ignition engine. So let's look at the effect of variables on the knocking, and this is the last slide on the SI engine knocking. Then we will continue with CI engine knocking. So let's look at increase in the variable. If we increase the compression ratio, what will be the major effect on unburnt charge? If we increase the compression ratio, the temperature and pressure will increase, and then the knocking tendency will also increase. So what action to be taken to avoid the knocking? You have to reduce the compression ratio. And can the operator control it? Can the operator control compression ratio? No, you cannot control it. What about the mass of the charge inducted? If you induct more charge, what will happen? The pressure will increase, temperature will increase, density will increase, and this will lead to more knocking. And if you want to avoid knocking, you have to reduce the charge of the mass that you are inducting. Can you change it? Yes, you can change it. How? By putting off your turbocharger, right? Inlet temperature. If you have higher inlet temperature, what it will do? It will increase the temperature at the end of the compression, and therefore it will lead to more knocking. So what needs to be done in order to reduce the knocking? You have to reduce the inlet air temperature. So can the operator usually control? Usually not, but in some cases you can. There are charge coolers. Okay. Combustion chamber, chamber temperature, chamber wall temperature. If it is high, then what happens? It will lead to increased temperature at the end of compression, and this will increase the chances of knocking. And if you want to reduce it, you have to reduce the chamber wall temperature or coolant temperature. So normally the operator does not have any control. These are all autonomous systems. Okay. Spark advance. If you increase the spark advance, then what happens? This is going to increase the temperature and pressure as we have seen in this case, which will lead to more knocking. If you want to avoid it, you have to retard the spark at once. Okay. In some cases, in special cars, operator can change it, but in most cases you cannot. Okay. In racing cars, for example, you can probably do that. Air to fuel ratio, if you increase the air to fuel ratio, that means more air and less fuel. This increases the temperature and pressure, because now you have to, in order to satisfy certain load conditions, you have to fix the fuel and you have to put more amount of air. So once you are putting more amount of air for the same quantity of fuel, then intake air density will increase, then at the end of the compression you will have higher temperature and pressure, right, and therefore you will have more tendency to knock. And this also gave you the answer for the question that you asked, where I said in lean charge will have more tendency to knock because of this reason. So what is the idea? You can make it slightly rich so that the excess air is minimum. In some cases you can do that, in most cases you cannot. Turbulence in the engine, if you increase the turbulence, this will decrease the time factor and this will reduce the chances of knocking. Okay. So if you increase the turbulence, knocking will be reduced. Okay. Can you control turbulence? Directly you cannot control, but indirectly by increasing the speed, the operator can control the turbulence in the engine. Engine speed, obviously engine speed will have the same effect as turbulence. This decreases the time factor and you can increase the engine speed. Operator can certainly increase the engine speed. Distance of flame travel, if it is higher, then what will happen? It will increase the time factor and it will increase the chances of knocking. What action needs to be taken if you want to avoid knocking? You have to reduce the distance of maximum travel. Can you control it? Can the operator control? Certainly not. This has to be done at the design stage. So I think this basically is the summary. If you have understood this, you have understood the knocking in SI engine. Okay. So let's move on to the next part, which is knocking in CI engines. So CI engine, as I said, CI engine we are dealing with liquid fuel which is being injected in the combustion chamber. So knocking phenomena is also quite different from what we experience in spark ignition engine. So in CI engines, injection process involve definite time interval. That means we have to inject for certain crank angle degree duration. Fuel cannot be injected all in one crank angle degree or half crank angle degree. It requires 15, 20, 30, 40 crank angle degree, certain interval. So that means you have to start at certain crank angle degree, and when you start, some first droplets will enter. Okay. So the first few droplets, they pass through the ignition delay, and the additional droplets are in the meantime injected through the combustion chamber. So when the first droplets are passing through the injection delay, more fuel is continuously being injected. So if the ignition delay period is more, combustion chamber will accumulate more amount of fuel. If the ignition delay period is short, you will have small fuel accumulation in the combustion chamber. So if the ignition delay is short, actual burning phase will start in a relatively short time after the injection. If the ignition delay period is long, the actual burning will start in a long duration. So relatively small amount of fuel will be accumulated in the combustion chamber when the actual burning will start, and the rate of pressure rise will be smooth. So suppose, for example, here you have start of injection and here you have start of combustion. So this is a small period. So a lot of fuel will not be accumulated, so rate of pressure rise will not be great. But if this period is too much, so by the time the first flames come up, there is a lot of fuel already available. So what will happen? There will be sudden combustion and sudden pressure rise, and that will lead to knocking. Okay. So you see here, this is start of injection, this is start of combustion, this is called delay period, and injection is continuing for a long period. Okay. So combustion and injection both happen simultaneously in a diesel engine. This is the another situation where, see this here it is small. So only this much volume is accumulated in the combustion chamber by the time the combustion starts. Suppose this is long, now it has become long. Okay. So here you see the more fuel is accumulated. So if the ignition delay is longer, actual burning of the first few droplets will be delayed, and fuel accumulated in this time will be higher in quantity in the combustion chamber. And when the actual burning takes place, all this fuel will start burning, and too much of rapid pressure rise will be taking place, resulting in jamming of forces. Piston is still, this is TDC. So you are already pushing the piston, and then suddenly there is a negative force in opposite direction with great rate. So this will lead to imbalance of forces, and that's why the knocking happens. So if this is too great, so here you didn't experience really the knocking, but if you really increase it too much, you will experience that there is knocking. Okay, so this is quite large here. So if the ignition delay is quite long, so much of fuel is accumulated, and it can lead to almost instantaneous pressure rise, result in violent gas vibrations, known as knocking characteristics by audible noise. In SI engine, knocking occurs near the end of the combustion, while in CI engine it is happening in the beginning of the combustion. This is one of the big differences in SI engine and CI engine combustion. Okay, so let's summarize the knocking in CI engines. So increase in variables such as C10 number will obviously shorten the delay period. Higher is the C10 number, shorter will be the ignition delay, and this will lead to less knocking. So effect of delay period, effect on the delay period, if the C10 number is higher, what will be the effect on delay period? This will be less, and this reduces the self ignition temperature. If you increase the injection pressure, this will also reduce the ignition delay, because the physical delay part of the ignition delay will reduce. This reduces the physical delay due to greater surface to volume ratio of the droplets, more number of small droplets, which will have more surface area for the same mass. Okay. Injection timing advance, if you start advancing the injection, this will also reduce, and the reason is reduced pressure and temperature when the injection begins. So this will also lead to reduction in ignition delay period. Compression ratio, if you increase, you will be injecting the fuel in hotter conditions, right, and that's what you want. Hotter will be the conditions, less will be the chemical delay of the delay period, or even physical delay will be reduced. So increase in pressure and temperature reduces the auto ignition temperature. If you increase the intake temperature, this will also reduce the delay period for the same reason. Jacket water temperature, if you increase, that will also reduce, it will have the same effect. Inlet pressure, if you increase, that will also reduce the. So all these 3-4 factors, they basically somehow accelerate the chemical reactions, they make the hotter conditions, high pressure conditions in the combustion chamber, which is going to reduce the delay period. Okay. If you increase the speed, this increases in terms of crank angle, this reduces in terms of millisecond, so this will reduce the heat loss. Okay. If you increase the load, so that means if you are increasing the load means what? You are putting more amount of fuel, so that means you are increasing the cylinder wall temperature, you are increasing the residual gas temperature, so this will also reduce the delay period. Okay. Then engine size, if you increase the engine size, then the delay period will decrease in terms of crank angle, it is not much affected in terms of milliseconds. Larger engines normally operate at low speeds. So larger engines normally do not knock that much, smaller engines have more tendency to knock. Type of the combustion chamber, it is ignition delay is lower for engines with pre-combustion chamber. So because in pre-combustion chamber you have very violent swirl flow available, which helps you reduce the physical delay part of the ignition delay. Okay. And so now let's compare. Now that we have studied the knocking in detail about SI engines and knocking in CI engines, let's compare them. So just look at this. This is SI engine. So here this is smooth. Okay. Combustion has started pretty smoothly, and then you see towards the end of the combustion you see vibrations in the P theta diagram. In CI engines, this smoothness of vibration is not there right in the beginning of the combustion. So in CI engine, combustion takes place in the beginning of the combustion. In SI engine, the knocking takes place in the end of the combustion, towards the end of the combustion. So in SI engine, auto ignition of the end gas takes place near the end of the combustion after the peak pressure. In CI engine, auto ignition takes place at the start of the combustion before the peak pressure. In SI engines, charge that auto ignites is homogeneous. So the intensity or rate of pressure rise of auto ignition is much more than in CI engines. CI engine, it's heterogeneous mixture. It's not homogeneously mixed. So knocking is very, very prominent in case of SI engines. Knocking is not so prominent in case of diesel engines. So therefore, it is called, knocking is also called detonation in SI engines. It is not when it is saying detonation, that means it is a term which is specific to SI engine. When you say knocking, knocking can be in both. But if it is detonation, detonation is only, that means you are referring only to SI engines. So no pre-ignition can take place in CI engine. Pre-ignition can only take place in SI engine. So because only air is compressed and ignition takes place only after the fuel is injected, just before TDC. So all those things that we experienced, details of many types of abnormal combustion that were taking place in SI engine do not happen in CI engines. So normal process of combustion in CI engine is by auto ignition. Therefore, rate of pressure rise in CI engines is higher than in SI engines, and audible knock is normally always present. So the audible noise, when becomes severe, lead to heavy vibrations and engine is said to be knocking. So in CI engine, you always have hard combustion. So that's why diesel engines always make much more noise than SI engines. But so that is not called knocking condition. When that hard knocking becomes really, engine starts vibrating and it becomes abnormally painful, then it is called knocking. Okay, that is what it is saying. Normal process in combustion in CI engines by auto ignition, therefore rate of pressure rise is higher in CI engines compared to SI engines, and audible knock is normally always present even in normal combustion conditions. The audible noise, when it becomes severe, this leads to heavy vibrations, and then CI engine is said to be knocking engine. Okay. So in CI engines, balance between normal combustion and knocking combustion is made. Okay. I will just give you, coming back to the SI engine, I thought I will just explain one term to you. You have seen octane number, but if you look at more detail of it, there are two types of octane number. You must have heard about it. One is called research octane number, the other one is called motor octane number. I will tell you what is the difference. So there are two methods that have been developed to measure the octane number in a standardized single cylinder engine, which is developed by CFR, Cooperative Fuel Research Committee, in about a century ago. Okay, it's still valid. CFR engine is 4-stroke, it's a 3¼ inch bore and 4½ inch stroke. Compression ratio can be varied, and there are many units. It can be normally varied from 3 to 30, but there are some units, for example, SI unit can be 3 or 4 to 11, and then CI units could be 10 to 30. Okay, so so you see, research octane number and motor octane number is measured in the CFR engine, both, and the engine is operated at standard conditions. What are those standard conditions? So when you are trying to find out research octane number, the inlet air temperature is maintained at 52 degree. In motor octane number, when you are trying to find out, the inlet air condition is 149 degrees C. The speed of the engine is 600. In this case, the speed is maintained at 900. The spark advance is maintained at 13 degree. Here it is advanced to 19 to 26 degree. It varies with the compression ratio. Coolant temperature maintained at 100. Inlet atmospheric pressure is 1 atmosphere, naturally aspirated. Humidity is maintained. Okay. So in 1931, octane number was isooctane was the most knock resistant hydrocarbon. But now there are fuels which are more than 100. So this was basically at that time designed to measure between 0 to 100 scale. Now of course there are fuels which go up to 125 or even higher. So let's focus only up to 0 to 100. So if you operate the engine under these conditions, whatever octane number you can measure, that's called research octane number. And if it is in this condition, if you measure in this condition, whatever octane number you measure, this is called motor octane number. Now can you tell me, just by looking at this table, which one will be higher and which one will be lower? Huh? Motor octane number will be higher. This is more severe condition. So these are all more severe conditions. Temperature is higher, speed is high. So the possibility of knocking will be higher in this case. So motor octane number will be lesser and higher octane research octane number will be higher. Okay. So when you test it, basically you run the CFR engine on test fuels. for both research and motor conditions, which I explained. Slowly increase the compression ratio until standard amount of knock occurs, which is measured by a magneto-restrictive knock detector. At that compression ratio, you then take the engine with blends of normal heptane and isooctane and try to match those numbers. So the octane number is the percentage volume of the isooctane in the blend that produces the same knock as unknown fuel. Okay. The anti-knock index, which is displayed at the fuel pump, is nothing but it's an average of the two. Okay. So on the fuel pump, if you say 91 octane, which one it is? Octane number or research octane number, motor octane number? Normally it is average of these two. Okay. So motor octane number is always lower because it uses more severe operating condition, higher inlet temperature and more spark advance. Okay. The automobile manufacturer specify the minimum octane number that will resist knock throughout the engine operating range. So whatever number, octane number is specified by the manufacturers, you should never put less than that. If you put less than that, then the engine will knock and then it may get even damaged. So this is just an example of knock characteristics of various fuels. For example, now there are many fuels. CH4 methane, which fuel we are talking about? Natural gas. It has a critical compression ratio of 12.6, research octane number 120 and motor octane number 120. Propane, which fuel? Propane, when we say LPG, it has 12.2 compression ratio, 112 research octane number, motor octane number 97. Methanol, CH3OH. This is upcoming fuel, is 106 octane research octane number, 92 motor octane number. Ethanol 107 and 89. Okay. Isooctane 100 and 100. 7.3 is the critical octane number. If there is a regular gasoline which is a blend of hydrocarbon, it could be 91 and 83. Or premium grade is 94 and something 87. Normal heptane, primary reference fuel, it is taken as 0. Okay. So the fuels with better anti-knock quality, fuel with anti-knock quality better than octane, the octane number is determined by this formula. Okay, this formula, this is a formula, empirical formula. Here MT is given, T is given. So what is MT? MT is milliliters of tetraethyl lead per US gallon. Okay, so you see here. This is no longer really valid because tetraethyl lead is normally banned all over the world. So we don't really use, but just from historical perspective, I thought I'll just let you know. So there are many chemical additives that are used to raise the octane number of the fuel. And the most effective anti-knock agents are lead alkyls, such as tetraethyl lead, tetramethyl lead, and these have been banned because there is a lot of lead. Okay. So this was introduced in 1923, tetramethyl lead was introduced in 1960. Now they are banned all over the world because the lead is put into the ambient air and this is inhaled by children and adults. And children, particularly the toddlers, when they are growing, they consume much more air per unit body weight. So they inhale much more lead. And lead really helps, lead really affects their neurological development. So many of the children of say 1980s or 1970s in countries like India and other places where tetraethyl lead was still being sold, they are mentally retarded. You must have seen in your neighborhoods also because of this reason, because we were putting tetraethyl lead freely into the air. 1992 is when we banned. Rest of the world it was banned in 1970s. We were late by 20 years. Okay. And then the oil companies came up with this brilliant idea of putting another chemical. This is called MTBE, methyl tetrabutyl ether, and this is now being put, and maybe 10-15 years from now people have already started doing research and tried to find out what is the ill effect of this on human health, and so it will now be phased out. They will develop something else and then 20 years they will make money. So this cycle continues. Okay. So in aromatics, toluene and xylene are the most likely candidates which are good solvents as an anti-knock additive or octane booster. So they are present in gasoline, no adverse effect to adding more is apparent. Then there now people are trying to study this organosilicon compounds. They are being investigated for additives. So knocking, as we know that knocking needs to noise and roughness. So when the intensity of the knock increases, a loud pulsating noise is produced due to development of pressure wave, which vibrates back and forth across the cylinder. It reflects from the cylinder head, goes back to the piston, and that leads to problems. The presence of vibratory motion causes crankshaft vibrations and engine starts running rough. It also causes mechanical damage. In most of the cases, knocking is local and very rapid pressure rise is observed with subsequent waves of large amplitude result in increase in rate of wear and erosion of the crown. So even the piston crown will be damaged when the piston is vibrating. Even the rings may get embedded and it will cause wear in the grooves. There will be more carbon deposits because of these vibrations. The combustion will not be really complete, and it will precipitate the carbon deposition in the engine combustion chamber, which will lead to other problems. Certainly, when you have vibrations, all the stagnant air layer around the cylinder, they get disturbed, and this increases the heat transfer. Minimum temperature in a detonating engine is about 150 degrees higher than non-detonating engine. So even the Tmax is higher. So if the Tmax is higher, obviously, more heat will go out from the engine combustion chamber, scoring away the protective layer of the inactive stagnant gas which is present on the cylinder walls, which will be done by these pressure waves. The inactive layer of the gas normally reduces the heat transfer by protecting the combustion chamber walls and piston crown from direct contact with the flames. Okay, this will lead to high heat transfer losses, and therefore it will lead to reduction in power output and reduction in engine efficiency. We have seen that if there are places where if the engine runs hot or if there are carbon deposits, it will lead to problems such as pre-ignition. Okay. So increase in local heat transfer causes overheating, especially of the spark plug, which may reach temperature high enough to ignite the charge before the passage of the spark, and it will definitely cause pre-ignition. And believe it or not, these are the pictures of the cylinder. These are the cylinder heads. You can see very severe damage to the gasket. You can see that whole of the piston top has melted away. You can see this is what happens to the piston crown. You can see lot of deposits on the cylinder head, carbon deposits. Okay, so this can really damage the engine, which is caused by a combination of high heat transfer and pressure, and in some cases it can be really, really bad. So if you have this situation, you can imagine what can happen. If you are flying an aircraft and this happens to your aircraft piston, the whole metal is blown. You will not be able to do any compression or combustion or ignition. Then you will be a dead meat in a matter of seconds. Okay? So I think with this, I complete the discussion on knocking and detonation on SI engine, CI engine. We covered the differences.